Okay, let's get started. All right, so we're going to talk about adding and subtracting fractions today, and we're going to start off with some really simple small fractions that have the same denominator, and we're going to work our way through mixed numbers and such. So let's start off here with our 2/5 plus 1/5. One way we can model this is by using these fraction wheels, and just imagine that they're perfect because these are not. So I'm gonna model 2/5 here. These have 5 pieces, so I'm gonna color in 2 pieces here and 1/5 here, coloring in 1 piece, and then we can count the total number of fifths we have. So the total number of colored fifths we have is 3. Over here we can take a look at the measurement model, and we would do this just like we would model whole numbers and integers here. So we're going to start off here and we're going to model 2/5. Well, this is 1, so each one of these tick marks is a fifth. So you can write them in if you like. I totally love the idea of kind of bringing home the idea of 1 is the same number over the same number. It's good to kind of start pushing that narrative early. So there's our 2/5, and then we're going to add another 1/5, and our solution here is 3/5. Let's take a look at the bar graph model here, and let's model our 3/5 plus our 4/5. So here is my 3/5, so 3 of these sections. And then here's my 4/5. Now when you do this kind of model, you can then say it's 7/5 right from here. But sometimes students need to see that all together. So it could be modeled this way, 3/5, and then maybe in a different color we can put in that additional 4/5, and we can also see there that we have a total of 7/5. Now I will warn you that doing it this way can cause some confusion because the students might think that this is out of 10 and not out of 5. So do be careful and make sure that you're clear that these are sets of 5 and things like that. Okay. All right, so let's get to the definition of rational addition with like denominators. If the rational number a over b and the rational number c over b, note that the denominators are the same, those are both b's, are elements of the rational numbers, then a over b plus c over b is equal to a plus c all over b. And so that is the definition of rational numbers, what we've already modeled. So what happens when the denominators are not the same? So here the denominators are not the same. Ooh, not writing very great this morning. Okay, so let's look at this. So if this was 2/3 and this was 1/4, how does that translate to put those two together on a model? Well, we can do it. Let me see here. Let me try to model my 2/3 here. Not the greatest. I probably should have practiced thinking about how I was going to do this, but this is how it is. We're rocking it now. And then if I model my 1/4, of course, it can't go overlap because this is already been used. So here's my 1/4 on this side. Then we can see that we're left with this one little slice right here. This is empty, so this one doesn't count. Since we're adding here, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is equal to 11 over 12. Now, we have to have a common denominator here. You can't compare things that are not of the exact same size, okay? So it doesn't have to be the least common denominator. It could be any common denominator, okay? But you have to be with that commonality when we're adding and subtracting fractions. So let's look at the formal definition of the addition of rational numbers with unlike denominators, okay? Now, this particular technique does require maybe an extra step to simplify the final remainder, but this works every time, okay? It says if you have two rational numbers, a over b and c over d, then a over b plus c over d is equal to a times d plus b times c all over b times d. And so kind of the idea here is, and if you can look here, you multiply the first numerator by the denominator of the second guy. So this is the a times the d plus, and then we're going to take the denominator of the first and multiply it by the numerator of the second, b times c, and then we're going to put it all over these two guys multiplied together because that is a common denominator. It doesn't have to be the least, it just has to be a common one. Okay, so there's kind of two methods here, and the first method I'm going to demonstrate is finding the LCM first. And notice that we've got multiple here to add. Now, we can find the LCM of all three of these and put it together. So let's see, we practiced LCM before, least common multiple, or let's not call it the least common multiple because now we're talking about dividends and divisors. Let's call it the least common divisor, and we're going to find the least common divisor of 4, 5, and 6. And I'm just going to remind you quickly how we do that. And what we do is we find the prime factorization of each of these numbers. So 4 is 2 squared, 5 is just 5, and 6 is 2 times 3. The least common denominator, which is the smallest number that 4, 5, and 6 will all divide into, can be found by taking the highest power of each of the prime factors that show up here. So our LCD here is going to be 2 squared times 5 times 3. All right, and that number is 15 times 4 is 60. Okay, now we're going to set this guy up here so that we rewrite each one of these guys in terms of 60s. And if I was working this problem, I'd do it all in one big hunk, but the truth of the matter is that we're modeling for young learners, not someone that's been doing this for a long time. Okay. So, what do we need to multiply 4 by to get 60? Well, 4 times 15 is 60, so 15, I'll have to do this, is going to be 15 times 3. 5 times what is 60? Well, 5 times 3 times 4, so 5 times 12 is what that's going to be. And then when we get down here to our 6 times 10 is 60, and we can see it here because 6 is a 3 and one of these two, so we'll need a 2 and a 5. That leaves us with 10, so we have 10 times 1. Alright, so let's see what we have here. So we have 45 over 60. This guy's 12 over 60. And this guy's 10 over 60. And then we're going to rewrite our problem here. Our problem was 3/4, so we have 45 over 60 plus 12 over 60 plus 10 over 60. And remember what the parentheses tell us to do. The parentheses have us grouped, so we have 45 plus 12, which is 57 over 60. Plus 10 over 60, going to give us 67 over 60. All right, so let's see the next slide here. Okay, so let's put these guys together. I know that changed pretty quick, but here we are. First things first, let's find our LCD, and here our LCD, we look at the factors of the first denominator, it's just x. The factors of the second denominator, it's just y. So the LCD is x times y. So when we convert our 3x, we're going to need to multiply that guy by y. And when we change our 4y, we're going to multiply that guy by x. So now when we put it together, we have 3y plus 4x all over xy. Now these guys cannot be broken apart from this point. The only way that they can be broken down is if we turn these into two fractions and then simplify each fraction. So this is the answer. Let's take a look here. When we take a look at our LCD on this one, we have a squared b. So what I always say is you write the first denominator down completely, and then look at the subsequent denominators and add what you're missing. So I already have the a, but I don't have the square on the b, so I need a second b, so that would be an a squared b squared. So to convert our 2a squared b into an a squared b squared, we need to multiply that guy, that 2, by a b. And then what do we need to do to our 3 over ab squared? Well, we need to multiply that by a to get an a squared b squared. And we can put these together. 2b plus 3a over a squared b squared. All right. So let's talk about mixed numbers. Mixed numbers is really something that really only happens maybe in the elementary grades, that you start phasing mixed numbers out when you get into algebra kind of ideas. So, you know, middle school kind of situation. But let's define one. A mixed number is the sum of an integer and a proper fraction. So here I have an example of 4 plus 2/5, and that is equal to 4 2/5. Now, this is a big confusion that students have all the time, because it seems as though addition turns into multiplication here. And it really isn't the case. It's not magic. Addition does not become multiplication. But it is true when we add this whole number that this is how it comes together. Okay? So here's the formula, and the idea is, and we'll do a couple down here, but the idea is that the whole number part is over 1 added to the piece. So this is the whole number part, and this is the fraction part. And that makes sense when you see how it's built up, right? Whole number and fraction. Okay, so we're going to start off by converting our mixed number into a sum here. Where'd my pen go? There it is. This is equal to 7 plus 3/5. And if we were to put these guys together, we have 7 over 1 plus 3 over 5. And now to put those guys together, we get the same common denominator. And in this case, it's 5. So this guy's going to have to be multiplied by 5, which is what it says it's going to happen right here. And so that leaves us with 35 plus 3 all over 5. So as an improper fraction, this is 38 over 5. Okay, and don't let the negative sign mess you up. This just means that the answer is going to be negative. So this is equal to -3 plus 2/5. That's -3 over 1 plus 2 over 5, and just like the other one here, because our bottom is 5, this guy doesn't have a 5 on the bottom, so top and bottom needs to be multiplied by 5. That leaves us with -15 plus 2, all that crap over 5, which is -13 over 5. Okay, so we've converted from a mixed number to an improper fraction. This is mixed number to improper fraction. All right, let's hit up another one. Okay, so how do we go from the improper fraction to the mixed number? We do that using long division. We perform long division with the denominator dividing the numerator. And so we set it up here. Here's our denominator. Here's our numerator. Here's our denominator. So the denominator dividing into the numerator. We do long division. We wind up with a remainder. So the quotient is the whole number. And then the remainder over the divisor is the fraction part. Okay, so rational numbers also use all the general rules of integers, so I'm not going to go over all of those rules, but I did want to point out a couple of them. It does include additive inverses and the distributive property. And I also wanted to point out that and I know I've said it before, and I probably will say it all the way through the end of this course, that students often find this very confusing here when we're dealing with a negative number, because the negative number can be placed outside, it can be placed on top, on bottom, or outside the entire thing along the line of the fraction bar, maybe slightly above or slightly below, but not obviously on top or bottom. So do be careful with your students, make sure they understand. And then also, of course, there's also the distribution of anything across the rational numbers. That also works. And I do also want to emphasize that a lot of students have this confusion even in college classes when they wind up in a situation where they have a plus, a minus. Plus a minus is equal to one big fat plus sign. Okay? It's just one big fat plus sign. Oh, how did I say that backwards? I was thinking something completely wrong. I apologize. Let me have you please go backwards for just a minute and understand, because I was thinking about this situation, which that is always a positive. So let me make this clear, because what I typed here was clear, and let me get my head in the game. When you add a negative, you can drop all of the positive here, because plus a minus sign is still a minus sign, so you get to drop all that extra stuff. My apologies, that was poorly explained, but I don't want to stop and start all over. So we continue with my flub. All right, so that brings us to this next theorem, and this theorem says that if A over B and C over D are elements of the rationals, then A minus B minus C over D is equal to AD minus BC all over BD. This is the exact same formula that we had for addition, but this is subtraction, okay? And we've got a couple of ways to do this, but let's do this practicing that LCD kind of situation. So the LCD here is 8. It's 8 because 8 is equal to 2 cubed. And 4 is equal to 2 squared, and we get the LCD from taking the highest power of the prime factors, and that means that it's 2 cubed. So that's what we have here. So 5/8 stays 5/8. And 1/4 is equal to how many eighths? 2/8. So now we have 5/8 minus 2/8 is equal to 3/8. Fractions do require more work. There is no lie about that. Let's take a look here. Couple of different ways that we can do this because it is a mixed number. I don't know where. I guess I'm going to add it in right here. I think I missed one of my examples earlier. Maybe it never even made it to my PowerPoint, but let me look at it here. So there's a couple of ways we can do this, and one way is to convert to improper fractions. So we can do that kind first. So let's take a look at that. 3 times 5 is 15 plus 1 is, we have 16 over 3 minus 4 times 2 is 8 plus 3 is 11 over 4. Then at this point we can determine our LCD is 12 because both of these guys are relatively prime, so it's got to be 3 times 4 because 4 is 2 times 2 and 3 is just 3, so it's those two guys multiplied together. Our 16 thirds is equal to 4 times 16 twelfths. And our 11 fourths is equal to 3 times 11 twelfths. Let me see if I can do this real quick. 4, so this is 64 twelfths. And this is 33 twelfths. So this now becomes 64 over 12 minus 33 over 12 equals 31 over 12. And then we would need to convert this back into a mixed number. And I'm going to do it over here. 12 goes into 31. 12 goes into 31. 2 times 24. 3, carry the 1. 7 minus 4. 11 minus 4 is 7. So this is going to equal 2 and 7 twelfths. All right, so what is the other way we could do it? Well, the other way is still requiring us to convert it into proper fractions, but not finding an LCD. So, ow. Golly, y'all. I apologize. Maybe I shouldn't be recording this morning. The other way is to do the whole numbers. Okay, and to do that, it's helpful to kind of stack them like this a little bit. You're going to see a lot of this kind of stuff. Okay, so we'll have the 5 minus 2, which is 3. And then we'll have the 1/3 minus 3/4. Now, yeah. Oh, y'all, I just totally screwed this up. Here we go. Here we go. Here we go. We're going to do this again because I didn't look at my notes and didn't pay too much attention. All right, here we are. We have our 5 and 1/3 minus 2 and 3/4. Let's get this done. Now, here's the idea. 1/3 is smaller than 3/4. I didn't notice this while I was going because I wasn't really paying close attention. So look, we've got to borrow here. And if I borrow from that 5, then what is it going to make that 1/3? It's going to now make that 4/3 because I'm adding a whole 3/3 to it. So now this fraction here becomes 4/3. All right, so let's see what is. Let me rewrite that because it's kind of messy here. So we have 4 and 4/3. Not with a line underneath it. Come on. Minus 2 and 3/4. Okay. Now we can make these guys have the same denominators here. This is going to have to be 12. So this is going to be 4 and 16 twelfths because we'll have to multiply this guy by 4 and 4 to get the 12. And this guy is going to need to be multiplied by 3 and 3 to get the 12. So this is going to become 2 and 9 twelfths. And we're subtracting these guys. So we have 16 twelfths minus 9 twelfths is 7 twelfths. And 4 minus 2 is 2. Personally, put them in improper fractions and go for it is how I always do it. But my apologies for that kind of very disjointed example. I hope I get my stuff together before this is over. Okay, so there is an alternative approach for students that are struggling with least common multiples. You don't really have to do the LCD situation, as we saw by the theorem. Technically, we don't have to have the least common denominator, just a common denominator, and then we can simplify the answer at the end. So let's take a look at this guy. So using the formula, and the formula says A over B plus C over D is equal to AD plus BC over BD. That's what we're going to use here. All right, so this is going to be 7 times 4 minus 3 times 8 over 8 times 4. 7 times 4 is 28, minus 3 times 8 is 24, all over 8 times 4 is 32. 28 minus 24 is 4 over 32. And then we have to reduce the fraction and give it in simplest form. And the simplest form here is 4 divides into both 4 and 32, so we have 1 over 8. Looking over here, we still have to convert our mixed number into improper fractions, so convert to improper fractions. So in this case, 5 times 6 is 30 plus 2 is 32 plus 5. Minus 3 times 2 is 6 plus 2 is 8. Now doing it using this formula here, and by the way, we put that minus sign in there as well. This works on plus or minus. This is going to be 32 times 3 minus 8 times 5, all over 3 times 5. Let's see, 32 times 3 is 96 minus 40 over 15. 96 minus 40 is 56 over 15. I'm not seeing where that's going to break down anymore, but you do want to reduce it anytime you can. 3 and 5 goes here. 3 and 5 does not go in the top, so let me turn this into a mixed number because it started off with mixed numbers, so you need to give the answer in the same form that the question was posed to you. So I'm going to do this real quick. Let's see, 4 15s is 15 and 15 is 30 is 60, so 3 gives us 45, left with 11. So our answer is 3 and 11/15. Okay, let's see what's next. All right, we're getting close here. Let's perform the operation and give the solution in simplest form. So we're just going to employ that formula that we've been using here. So this guy is going to be 7 times x plus 4 times 3x over 4 times 7. So that looks like 7x plus 12x over 28. And because both of these are x's, they're like terms, we can put them together. So we have 19x's over 28. Looking at this guy and doing it the same way, we'll have 1 times 2x squared minus 1 times x over x times 2x squared. Now this is going to have a little extra step. This is when finding the least common denominator is really, really helpful versus a common denominator. So this gives us 2x squared minus x on top with a 2x cubed on the bottom. And you can notice that there's some extra x's up here. There's more x's. So we can actually pull an x out. Over our 2x cubed. And now you can only cancel things that are multiplied here. So we've got this x can cancel with one of these guys, leaving 2. And our final answer is 2x minus 1 over 2x squared. Now, that required us to know and remind ourselves of a lot of algebra rules that our students aren't going to know right off the bat. So it's up to you to be able to inform them that it's going to be the best for them, even though it's easiest to go for the common denominator. Once you start getting into things that are algebraic in terms, it's not as easy to pull out a common factor out of the numerator and the denominator. So I would really suggest that it would be better to do this problem with the LCD. And here, to find the LCD, we write the first denominator down completely. And then we look at this denominator. What do we need? Well, we need a 2, and we already have one x. We need one more x. So this is actually, the LCD is actually 2x squared. And then we could work it like this. 1 over x needs to be multiplied by something to have 2x squared. And the 1 over the 2x squared is good. So here we need to multiply this by 2 and x. Now, when we do it this way, we can put it together very simply. 2x over our 2x squared minus 1 over our 2x squared is equal to 2x minus 1 over 1, 2x squared. So you can see that there's a lot of extra knowledge that you need to use sometimes when you're not finding that least common denominator. Okay. And finally, let's talk about the estimation with rational numbers. The best way to do perform estimation with rational numbers is to kind of like round in your head, kind of like bring those numbers to the next benchmark number. Things maybe like a quarter, a half, 3/4, 1. Those would be those benchmark numbers that you're going to want to kind of look at. And so if we take a look at this first one right here, 27 over 13 is a little bit more than 2. And 10 over 9 is really close to 1. So this estimation would be 3. And do we think that that is a high estimation or a low estimation? Well, this is a high estimation because to be 2 here, it would be 26 over 13. So we got 1 extra and 1 extra. So it would be a high estimation, just FYI. Okay, and then over here, let's look at this 3 and 7/8. 7/8 is very close, very, very close to 1. So this would be 4. This is an 11.5, and this is a 2 and 2/5, and 1/2 and 2/5 are pretty darn close, so we could make that a 1. So then we would have plus 11 plus 2 plus that 1 from their fractions, and 1/16 is very small, so we would ignore it because it's close to 0. So we have here 15, 16, 17, 18, 19, 20, 21, 22, 23. So our approximation is 23. And would you say whether this guy was high or low? I'm going to say that this guy is low because we rounded up. We rounded up more than we ignored. Okay? All right. Well, I hope you guys have a great day. Thank you.